Yes, so I would like to invite the third speaker for the session, Nisheeth Vishnoi. And it is wonderful. Okay.
Hi, I'm here.
Hi. So the last talk is about a survey of recent advances in algorithmic fairness. And this is going to be a long survey talk. And the author is with Yale University, is professor at Yale University, his area of interests are foundations, computer science, machine learning, optimization. He wrote an amazing number of surveys and books, including algorithms for convex optimization, faster algorithms via approximation theory, real stable polynomials and their application to theoretical computer science. And he's together with Elisa Celis, heads a research group on controlling bias in AI at Yale. Okay, thank you.
Thank you, Nicola. So thank you for the invitation. I was looking forward to being in Zurich, but here we are in meeting each other online. So this talk is going to give you some flavor, of this emerging area of algorithmic bias. This is a very, very big area right now, which includes many disciplines which go far beyond computer science, as the problems that we are facing go beyond computer science. But at the end of the day, these are problems about algorithms. And so what I'm going to present in this 1 hour is a survey of the work that we've been doing, which also includes some of other people's work, as to how to redesign algorithms where we can control for specific kinds of biases. And this is joint work with my colleague Elisa Celis and a whole bunch of other collaborators from all over the world. Okay, so I'll just start very quickly. I guess it doesn't need a lot of introduction that there's bias in algorithms. Here are a couple of examples for you to look at. So the first, and I think one of the motivating examples for this talk is if you go on Google Images and search for, let's say, CEOs, you get to see a picture like this. I mean, this is a collection of largely of men. What's the issue with this image? This was a study done by K. Matuszek and Munson. They found out that Google Images, for instance, systematically misrepresents the fraction of women in searches like these. So not just CEOs, but other professions as well. A now famous paper by Joy Bulwami and Timnit Gebru showed how facial recognition systems, for instance, those developed by many big companies, are biased against minorities, biased against women. The error in their, the difference in the accuracies are significant. And also something that we all deal with, when we go on Google and search, we see these ads on the side. I don't know if many people look at them, but it's a known fact by now that women get shown, ads, or women are more likely to be shown ads for low-paying jobs as opposed to high-paying jobs. So I don't think any of this is coming through a conspiracy of people trying to be biased. And the question that people started wondering, is why is this happening and how can we curtail? First of all, what is the problem with this? One can argue that, okay, this is stuff on the internet, who cares? I mean, we know that this is not reality maybe. But there's a problem with this, and the problem is that biased algorithms can alter perceptions, and this is a very important point. In the same paper, K. Matuszek and Munson also observed that showing people images or results which misrepresent, for instance, gender ratios, forms their opinion or changes their opinion about what reality is. And if this example was not convincing, I don't have to go much further than our regular Facebook or newsfeed experience, where we are experiencing this in real time. how information which is presented to us by algorithms which select this information, personalize it for us, how the worldview, how the same world is presented in very, very different ways to people with slightly different views, and how these opinions are slowly getting more and more polarized, and at the end of the day, disrupting democracy. So this is a real problem. It's not just something that exists on the internet, and we can, as long as we shut off the internet, you'll be, away from it. It is affecting us, and so there is a need to control it. So let's get to let's try to get things more concrete and more mathematical. But before that, I'd just like to point out this kind of a cycle which exists in the system. So really, many of these problems, as we will see some examples of this later in this talk, start off with some high-level problem in the real world. I mean, what do you do on Google Images? You say, I want to see what a CEO is. Now, this is not a well-defined objective, okay? It includes data or input. I mean, so so there are images in the real world. They have been chosen. I mean, they have been put on the internet by a select set of people. So there's an issue related to selection. There's an issue related to how we represent these images. There's an issue related to how measurements are made, and I'll talk a little bit about it in a second. And algorithms work with this data or input, but they also essentially solve some kind of a constrained optimization problem at the end of the day. So Google's image search would say, okay, I want this, here is Nisheeth, he searched for CEO. I want to show him some images which are representative of CEOs. So how do I do that? So they probably optimize some objective function of the input subject to some constraints. And this is where the modeling choices that we impose on the algorithms play a role. And what you see at the end is really the algorithm, but the choices have been made before. So there is a real world, which is already probably biased. It is biased. We select some data from it, which could enhance bias. We have models which seem like they have nothing to do with bias, but they could also exacerbate bias. And then the point that I made through my previous two slides is that these output of these algorithms is consumed by individuals or feeds into other algorithms, which then goes and affects the reality itself. So I think this cycle is missing. Maybe it'll come out. Yeah, there's some animation issue here. But let's look at an example of a problem classification. So imagine that you have individuals where, for this simple setting, I have just put them around two axes, income and education. So this is a choice of representation that we have made about the individuals, that we are choosing to represent individuals through how much they earn and how much they're educated. So our goal might be to decide how creditworthy they are, or how likely they are to succeed. And these things start serving as proxies for our end goal. And what do I mean by modeling and constraints? Well, I mean, here you can look at, I guess people in machine learning know what I'm talking about. But if not, then you could constrain the search of the classifier to be, let's say, a vertical line. So that maybe you just choose to decide whether to give someone a loan or not based on their income. It could be horizontal lines, or it could be something more complicated, or as these days we use, deep nets, which give amazing power, modeling power. So I guess, yeah, here comes the cycle. So this is an important picture to, I think, understand before one starts working in this area, that we are dealing with algorithmic and modeling choices which are creating this issue or making this issue worse. To be a little bit more concrete, I guess, I think I already mentioned this in the previous slide, but we associate numbers to people. For instance, here this person is associated with two numbers, 5 being, let's say, the income, and 10 being some measurement of education. We often also have outcome variables associated to these, to the mathematical representation of these people. And then we have these model choices. So what are possible sources where bias could creep in? Because if you want to control bias, we need to understand where all it can come in from. And the first and foremost is the real world itself. I mean, we are a production of hundreds and thousands of years of various societal and historic biases. Then how do we choose to measure people? This measurement often ends up being correlated with things like gender and race. I mean, if you notice in that picture that I showed you, the women were kind of on the lower quadrant of that image. That was not some mistake, but that's how I drew it, to point out that historically, if you look at the income, women will be on the lower axis, and if you look at education, women will also be towards the lower part of the thing. So the choice of representation or measurement brings into, lets these societal and historical biases creep in. Then I guess this is something I think many people understand, that when we have input or data, we want to make sure that we don't under or over represent particular groups. But believe it or not, until very recently, and even probably now, this is not something that all algorithms take into account. And then finally, modeling choices, which we will focus on in this talk. So what kind of interventions can you think of? Roughly, there are two categories of interventions. One are called pre-processing methods, where you work with the inputs. When you get the input, you change the input, and then you feed it to an algorithm. Okay, so that's one approach. So you have some ground truth, you know what the reality is, and you have a goal, you have a fairness goal. So, and once you get the data or the input to your algorithm, you try to pre-process the data before you feed it into the algorithm. This may or may not work, but people definitely try this. The other, and I think more richer community working on, richer set of people working on, is when we kind of constrain the algorithm and the model to ensure fair outcomes. So irrespective of what the data is, or you could try, multiple approaches, combine them and so on. So this is really the landscape of the algorithms, pre-processing methods and in-processing methods. So the latter ones are called in-processing methods. And there's also a class of methods called post-processing methods, but that's not particularly popular, but there are examples of that as well. Okay, so but before I go into, so this talk will be about the second methodology, but before I go into this, I need to talk about fairness. And here, this in itself could take an hour easily to talk about what is fair. But let me just tell you that there are roughly two extremes for fairness. One is the notion of individual fairness, which is grounded in this idea that all individuals should be treated similarly, which many of us would like. And one notion is that of group fairness, which is where different groups should receive similar or proportional treatment. And so far, the examples of fairness that I have talked about have to do with group fairness. We talk about equality between men and women, or equality between races, and so on. And there is a tension between various notions of fairness, not just a social tension, but also a mathematical tension. You can prove that, and this was proved by Choldachova and also Kleinberg, Malainathan, and Raghavan. It's a pretty simple thing, but nevertheless, they observed it, that you cannot have a single algorithm, in this case, a classifier or something like that, which would be fair with respect to multiple notions of fairness. So you can't produce different notions of fairness and have, so that any algorithm can be fair with respect to one, but not necessarily with respect to the other. And there are many definitions of fairness which are actually relevant. They depend on the context. So context plays a key role, in fairness. So anytime you have a problem, you should ask yourself, what is the context? What is the right definition of fairness that we are talking about? You should also look at the book by Solon Barakos, Moritz Hart, and Arvind Narayanan on a thorough discussion on fairness in machine learning. Okay, so I'll give you a 2-slide version of what these definitions roughly look like. So we're going to focus on group fairness, and even in group fairness, there is a bifurcation of definitions. And the first set of definitions are what are called outcome independent definitions. So let me explain what these are. So imagine that you have a set of items. So these could be people, these could be web pages, these could be news articles or whatever. And you have a partition, not necessarily, let's say a partition, but let's say you have a collection. So, I mean, this is really a hypergraph. This is a theory audience, so I can feel comfortable using some theory language, but you have a collection of subsets. In this picture, I've drawn them to be non-overlapping, so a partition, which are these different groups with respect to socialization salient characteristics. For example, here you could think of it as race. And in all of these problems, essentially, at some point, it boils down to selecting a subset. Okay, so in one way or the other, the starting point is always a subset selection of some kind, or multiple subsets, but let's say one subset. So you want to select a subset S, the algorithm wants to select a subset S. And let's say if we have Ni be the number of items from the group I that are selected in the set S. One observation is that many group fairness metrics are functions of something like Ni or Ni divided by the size of the group, or something. I mean, you get the idea. That it is not taking into account anything other than the structure of the groups. It is not taking into account what the task is. And that's why these are called outcome independent group fairness metrics. So for instance, something that we all know is equal representation, that we would like to select a subset where each group is equally represented. I mean, this is a notion of equality, which is quite universal. Proportional representation, which is something also I'm sure everybody here has experienced. This now says that we want to select number of people proportional to the group size. Okay. Or yeah. And I guess a more technical and more legal fairness definition is what is called the 80% rule. This is something which is actually a law in the US. What it roughly says is that suppose you have two groups, men and women, and you end up selecting, and you're looking for, hiring people from there. So if you select more than 8 men out of 10, then you better have a very, very good reason why you're doing that. And it's not just, it's a law in many settings in the US here. And all of them can be encoded as equalities or inequalities involving these numbers. And so this is something, I think, an important thing to keep in mind. They don't take into account the outcome, so they are called the outcome independent fairness metrics. Let me give you this other class of definitions, which are called outcome dependent. And here again, I mean, the setting is the same as before. You're given a set of items which are divided into groups. You want to select a subset, but there's also an ideal subset, which I call S star. Okay, so this is important in some problems. For instance, this could be the set of people who will not commit a crime again once you let them on bail, right? Or something like that. You can pick your context. And now the quantities that start becoming important are not just these numbers, functions of these numbers Ni, but also functions of these numbers M sub i's, which are the number of items that you select from the ith group restricted to this S star. Okay, so let me give you an example. Something called the true positive rate, and there's an explosion of these things. You can totally imagine that you can look at selected, not selected in each group, and you already start getting, various variants of this. So equal true positive rate says that for every I in J, the ratio of people who you select in your set S, or the number of people, number of people who you select in your S, which belong to S star, divided by the number of people you select, should be the same across all groups. Okay, so that your positive rate is the same for each group. But you could easily look at the complement and come up with negative rates and false positive and so on. And that's where all these definitions start exploding. And a lot of initial work in fairness in machine learning was focused on classification, which I'm not going to talk about in this talk, but was really looking at each individual metric and designing a specific algorithm for that metric. Okay, I think this was clear to people that you can't design algorithms for all metrics. So let's pick a metric and design a new algorithm for that. Let's pick. So, and this is exactly what we are going to bypass, and that's one of our main contributions. But before I go into that, this is these kind of things are called outcome dependent, precisely for the reason that they also depend on this outcome S star. So I'm going to tell you our group fairness framework, which from what I just said follows quite easily. And I'm just going to tell you this in this context. It is more general than this, but let me just talk about the simplest context, where what we do is something which is very obvious. We say, okay, instead of worrying about each fairness metric, let's consider the following class of metrics, where you as a user specify a lower bound and an upper bound for each group. And my goal would be to select a subset S which satisfies these intersection conditions. Okay. So this is not really a new fairness definition, because it requires additional parameters, the lower bounds and the upper bounds. But one of the observations that we have, which is made clear in this paper with Celis and Keswani and Huang in 2019, is that these constraints can encode a large number of constraints or metrics that I talked about in the previous two slides. Some very simple examples are, if you want like this 80% rule, you could set the lower bounds and upper bounds to be some value X, and for that particular Li, you can set it to be point X. You can play around with this. I think that's something to think about. But okay, so why these constraints? Why the choice of these constraints? So one reason for the choice of these constraints is actually from the forethought or the foresight that at the end of the day, we are going to add these constraints to some algorithms, and we would like those algorithms to be still reasonably feasible computationally. So we can't really add very, very complicated constraints. And some of the constraints I talked about in the previous slides are actually nonlinear, and all kinds of nasty divisions are going on there. So the hope is that these constraints are simple algorithmically, as well as they are flexible and general enough to capture a host of fairness metrics that people can care about. And the way we would use them is by saying, you come to me and say, here is my fairness metric. I'll say, okay, I'm going to set LIs and UIs in this specific manner, and then pass it on to the algorithm, which will then solve some optimization problem with these constraints and ensure that the end outcome is guaranteed to be fair with respect to your given metric. In some sense, these are meta algorithms. Okay. And we have applied this frameworks approach to a variety of problems. I guess the starting point for us was determinal point processes, which Santosh almost spoke about. I'm glad he didn't, so that I have something to speak about. Data summarization, this problem arises in data summarization. I'll talk about it, so I don't want to say much about it here. And then ranking, which is once you have a collection of images to show, the order in which you show them also matters. This affects people's perceptions. So ranking is a very, very important component in online, in the online world. We use this, and that involved the bipartite matching problem, a new variant of bipartite matching problem. We looked at a certain multi-winner election problem, which was motivated by an election that actually we conducted in the canton of Valais in Switzerland, where it was some kind of a constrained submodeler or maximization problem. We looked at this example of polarization, which is really this the red feed, blue feed example of Wall Street Journal, where the underlying optimization problem was bandits, and we gave a constrained bandit optimization algorithm. Classification is the place where we kind of really showed the power of our framework, where we had a single algorithm which was competitive with a dozen other algorithms at the same time. This has been deployed by IBM in their AI Fairness 360 tool. You can look at it. And something I heard Pravesh talking about, Myers and auctions. This again, has been used in online advertising, where bias has been reported. So what we did was we came up with a constrained version of Myerson auction and kind of generalized Myerson's result in this setting. It does generalize beautifully. And a very recent work, which is now looking at pre-processing data using constrained optimization methods as well. And if you want to look at some of these results along with their accompanying demos, you're encouraged or welcome to go to this website listed below. So with this, I'm just going to first give you a high-level view of what our strategy looks like, and then delve into a couple of examples from the previous slide. So this is a picture of what, okay, so this is what people were doing before. You have data or input, you optimize your sample, and you give an output. Now you have these additional constraints. So the task of optimizing is no longer obvious. In fact, in some cases, as we're going to see, the problem turns out to be very hard computationally. So there is a computational price associated to being fair. And then there is a question of, because you're adding constraints, the output is no longer the same. I mean, you're constraining the input space. And there's a question of how much are you losing in that? I mean, if you're a company like Google, say, okay, I'm willing to add these constraints, but can you tell me how much of the revenue or click-throughs or whatever that I'm getting, I'm going to lose. And here we have an interesting twist at the end of the talk I'm going to talk about, that it's not something very counterintuitive, that by adding constraints, actually you can increase the utility. This sounds like nonsense to people sitting here at this point, and I'm going to come to this at the end of the talk. So this is where we are, and it's studying this pipeline. And let's come to a concrete example. So we're halfway through the talk. If there's some urgent question, I'm happy to take it now. Otherwise, we can also just wait till the end of the talk.
So there's a couple of questions that you may want to answer now. Do you consider overlapping of disjoint groups here?
Yes, in our framework, we do consider overlapping groups. Yes. Okay. Yeah, that's very, very important, because often bias is actually intersectional. You could be, let's say, a Black woman and be much worse off compared to, let's say, just being a woman or just being Black. So in fact, this IBM example that I showed to you in the beginning was the error in accuracies for black women versus white men is super additive.
Yeah, and there's a second question. How does the algorithm designer avoid the bias of having groups whom it aims to help, for example, women, and concentrating on their losses, for example, salary?
Sorry, could you repeat that question?
Okay. How does the algorithm designer avoid the bias of having groups whom it aims to help, for example, women, and concentrating on their losses, for example, salary, while choosing or being coerced to ignore their gains, such as kind of work and danger?
So I'm not sure I understood this question, but I think there is a partial answer to this, which I'll come to the end of the talk, that often by making the process fair, you might actually be improving the utility for everyone. And I think the key, I can give you the punchline now, the key is that even though we are doing constrained optimization, it feels like the objective will go down. But the resolution is that what we are optimizing is already biased. You have a cost function. The values of those may already be less for a particular group compared to their true utility to you. And I'll explain this at the end. So I think hopefully if still not answered, then I'll come back to this question.
Yeah, I was also trying to, I'm not sure exactly what the meaning of the question is. So,
okay.
But
okay, so shall I continue?
Perhaps I just read it badly. So there's maybe a last one, very quick, or I don't know whether it's quick enough, at least it's short. From an application, say societal point of view, how do you avoid creating a bias created by the definition of the subsets?
That's a very, very good question. And this is why this area is wide open. And how do we define a subset? And I guess in these examples that I'm going to talk about, there's an even more bigger issue, which is kind of related, which is that do you even know where an individual item belongs to? So in the case of, let's say, men, women, it might be easier to answer this question. But when you talk about documents, let's say newsfeed, and you're talking about left-leaning and right-leaning, there is a probability that something is left-leaning or right-leaning. There's always noise in these group labels, which could be because maybe people don't identify themselves fully as men or women, or it could be because we just don't know for sure whether a particular item belongs to this group or that group. And that creates this problem of doing kind of constrained optimization in this very uncertain environment. And that's something we are actually currently working on. And we just have a paper which we put online a few days ago. So I'll again mention this at the end of the talk. Okay, so yeah, these are all really nice questions. So I'm going to talk about data summarization. And again, kind of showing you how the problem starts, right? So the problem is the following. I mean, you have billions of images which are tagged, let's say, scientist. And now there comes a user and you want to show them a subset of these. If I go and search for a scientist, I can only see a small number of them on my screen. And this is the real problem that Google Images has to solve. So the point being, the problem is ill-defined to start with. There is no clear problem, okay? So this is very, very important to note. We are all very mathematical people. We somehow have this thing ingrained to us that problems come in a very mathematical form. And that's exactly what I'm trying to point out, that that's usually the starting point of where bias starts to creep in. And we're gonna see this here. So the high level goal is kind of, your manager comes and say, hey, Nisheeth, I want you to come up with an algorithm which solves this problem. What is this problem? Okay. Why is this useful? Well, it's useful for summarization. We all consume information on the internet, but also used in training. I mean, often people take these samples and then train algorithms on that. So it's for end use as well as plugging these things in for training. So as a mathematician, I would say, hey, let's start with the following, right? Let's associate a vector to each of these images, and let's define some kind of a diversity function, and which gives a value given a bunch of vectors or a set of vectors, which gives associates some value, which I think of as diversity. And then I could either find a set which maximizes the diversity, or even better, output a set with probability proportional to the diversity to be more robust in some sense. So then the question arises, how do I convert these things into vectors, images into vectors? Okay, first of all, images are already biased. There is a specific set of people who have been photographed. I'm sure that this set of photos is not representative of the entire planet and the entire range of scientists. But then on top of that, there is this black box algorithm, which is usually has something to do with deep learning or convolutional neural nets, which takes these JPEG or whatever raw images and converts them into some feature vectors. Okay, this is a source of bias for sure, because this black box already is trained on some other images. So I don't think anybody really understands how to deal with that. Okay, so we have a bunch of vectors. We encode them as a matrix. So think of this as a fat matrix. The columns are the images. And we would like to select a subset of these vectors to show it to the user. How do we define a measure? And this is a really tricky and difficult question. We want to find a measure so that we can solve some of these computational problems easily. And at the same time, we want it to capture the high level notion of diversity. So if you had two vectors, then I think this problem is simple, or at least many people will come up with this idea that for two vectors, you can think of that they are same or similar, how similar they are by looking at some function of their inner product, right? For three or more vectors, the problem becomes a little bit more complicated. You can look at correlations between pairs of vectors and then define a metric based on that. You could do many, many things actually. But here's something that I will talk about, which is to look at the parallel pipe formed by these vectors and look at the squared volume of this parallel pipe. This is a weird metric. Okay, if you have never seen this before, yeah, you would not probably come up with this metric. But it does have some nice properties which, quote unquote, capture diversity. If the vectors are in the same plane, then the volume is 0. If the vectors are orthogonal, like in the second image here, you see that the volume is large. And mathematically, this is the definition of this function. It's a determinant of this matrix restricted to these columns transpose itself. And this has a name. These are called determinantal point processes. They're very well studied in mathematics, in physics, and in machine learning. Their use was what's the word? Use was
pioneered.
Pioneer. Yes, thank you. By Kulesha and Taskar, who use it for images, videos, and documents. There's a very nice survey on this. That if you're interested, you can read about it. The point I want to make is that all of these choices are man-made or human-made. How we convert images to vectors, how we choose a metric of diversity. And we typically don't, as algorithm designers, at least, I mean, I can talk about myself, right? My training did not make me reflect enough upon the choice of these objective functions. And of course, not all algorithms are equally important. So one should keep that in mind. You cannot stop and start thinking about every possible algorithm in this manner. But some algorithms are more important than others. Okay, so this has this nice property. Well, okay, so I think the reason for the choice of this metric, let me just give you the punchline, is that there are very fast algorithms from people such as Santosh Vempala, who you can sample such sets. It's called volume sampling. But in fact, this is kind of the first paper well, my first paper actually on unfairness, where we saw if this notion of diversity also encapsulates combinatorial diversity, which is, does it also diversify in the space of race or gender? And puzzlingly enough, the answer was no. Don't fully understand why. Is it the case that all vectors of women are slightly lower in every dimension than men, so that when you have an opportunity to select, you select a longer vector, and then because they're close, these get ruled out? I don't know. But the why this was happening was not clear. But we did definitively observe that in this empirical paper in FATML in 2016. And I guess to give you a sense of the problem is feasible. I mean, the first image, first row of images is diverse, possibly in this notion of volume, volumes in the volume space. The second set of images is kind of diverse in race and gender, but it shows only one dimension of scientists, I guess, those who work with test tubes. I don't. And probably what you're looking for is the kind of third row is what you want to show. Okay, so mathematically, what we did was we said, okay, we don't understand why this measure of fairness, or diversity rather, this measure of diversity is not treating men and women equally. How about we impose this condition? And here's one way to impose this condition. We can say that you give me these numbers. So this is a specialization of this framework that I talked about earlier. You give me these numbers, let's say K1 and K2 in this case, and ask me to pick K1 images from the men and K2 images from the women. Now, what would be the objective function? The objective function, it turns out, is the following. That what we would like is so we want to associate still a probability to a set, right? So probability to a set is still proportional to this determinant of Vs transpose Vs. And this is not a choice that is arbitrary. In fact, you can show that among all distributions whose support lies on sets which are fair in this K1, K2 sense, this is the distribution that is closest to the original distribution, where we use the KL divergence as a metric of closeness. So, okay, so there's a mathematical reason to choose this. So the problem becomes, which is called DPPs with partition constraints, where you have, you're given a family of subsets, which are quote unquote fair sets. They could be arbitrary, but in this case, they are just partitions. And your goal is to sample a set from this with respect to this probability distribution. So VSs, the vectors VSs induce a probability distribution on sets. So there are two inputs, the sets and the probability distribution. So there are, for people who know matroids and stuff like that, you can already see that this is some kind of a matroid intersection. One matroid specified by the partition constraints and one matroid specified by the vectors. Okay. And in fact, this problem was already observed by Kulesa and Taskar, not from the point of view of fairness, but from the point of view of resource constraints. I mean, you may have other resource constraints that you would like to impose on your diverse sampling. And they had this question about, can we sample this problem? Okay, can we sample from this distribution given this input? And oops, this looks okay. So now I'm going to tell you in one slide what our result is. It builds up on this work of Ben Ho et al. And Deshpande Vempala, which are fast and exact algorithms for unconstrained DPPs. The first thing we observed was that once you start adding these partition constraints, which look very simple, the problem becomes very, very hard. In fact, it's even harder than permanent in some sense because it captures mixed discriminants. So that's where, you know, this price of computational price of fairness kind of hits you. That it's nice to say that, yeah, I'm willing to add these constraints, but then the complexity explodes suddenly. We did give a polynomial time algorithm when the number of parts is constant, but it was really a polynomial in the bad sense that its exponent was too high for it to be of practical use. So what we did was something really simple. We come up with a linear time solver, which was inspired by this work of Deshpande and Vempala. And we proved that under some natural balance property on the data, we proved two things: that the distribution that we sample from is close to the distribution that we would like to sample from, and that the price of fairness, the difference between the distribution, the target distribution, or the output distribution and the unconstrained distribution is also small. So the condition on data looks something like this, that if we look, so for instance, in two groups, so the red vectors belong to one group and the blue vectors belong to one group. So you could look at the singular values of the matrices associated to the red vectors and the blue vectors, and then kind of enforce that they don't look like the first picture that you see on your left, the picture labeled A. That it should not be the case that all the women vectors are pointing in one corner and all the men vectors are pointing in that corner. As long as they are reasonably intermingled, which is what picture B looks like, and is mathematically captured by this beta balance condition, which is not important for this talk for you to understand. It's some kind of a balance condition in the data. Under that, we could show that the following simple algorithm works. And the algorithm is the following. And this, I think, is something that many people should be able to understand, that as long as you have a requirement from a part, so let's say there are two parts, you needed K1 from one and K2 from the other. So you still have a requirement from the first group, so you go there, you pick a random vector from this class with probability proportional to the squared current length. And once you pick that, you subtract off that vector, or you subtract, basically you project all the vectors orthogonal to this chosen vectors. And when I say all, I mean including from the classes where you have not even picked. And that's what induces correlations across these different groups. So the algorithm ends up being really, really simple and practical at the end of the day. It comes with some theoretical guarantees. And so you can argue whether these guarantees are reasonable or not. But it's practical. Making it theoretically work beyond partitions is a challenging problem if people are looking for one. In practice, it works. And let me just show you this slide. I'm not going to talk much about it, but what happened is that when we started looking at this problem from a more mathematical, more theoretical point of view, we realized that there are several new problems, theoretical problems that arose from just this setup, where you have, so DPPs have a very close relation with polynomials. So you could formulate the problem of you're given an evaluation oracle to a polynomial, and you're given a separation oracle to some polytope B. And the problem that I formulated in the previous slide is really just the following thing in green, where you want to output a set S from this family B, where the probability of outputting is proportional to the coefficient of the set in this polynomial. This was purely motivated from this previous setting, and it led us to some very interesting results, including connections with real stability, Gurwitz's result on capacity, and all kinds of stuff, which is totally unexpected. The point being that sometimes these kinds of excursions can also lead you to some interesting problems. At least it led us. So it's nice to have that in mind. Okay, and we have a demo in case you're wondering how this works. You can go onto this website and look at, so you have your own controller. So as a user, now you can control for let's say gender. And you can see how the search looks like. Let me move on. I think I have 10 more minutes. So let me quickly go through this example and then I'll end. So rankings. So here, now that you have chosen a subset, the problem is to order these images. And the ordering is important because we know that the way human eye processes information, it's not the same. Every spot on the screen is not the same. There is an ordering. And so the high level goal again becomes to output a utility maximizing ranking. And again, the black box, the additional black box that comes here compared to the data summarization problem is something which tells me at the jth position, what is the utility of placing the jth item. Okay, so this is, we assume this is input to the algorithm. Again, the choices that we make. So what do our fairness constraints translate to here? What turn out to be sufficient? What turn out to be sufficient are the following. So this becomes the following problem. You're given m individuals to rank in n positions. You have some utility matrix. And so the constraints are the following. These are non-overlapping, these are possibly overlapping groups. You have G sub L denoting the individual belonging to group L. And in this example here, I just put upper bound conditions. And our framework translates to saying that in the top K positions, you restrict the number of elements from each group. So U sub LK is the number of elements you're allowed in the top K positions from the group L. Okay. And the goal then becomes to find a ranking which satisfies these constraints and maximizes the utility. And here's an example, I guess. These are the positions A, B, C, D, E, F. These are the people. I guess you can tell which are the women, which are the men, and these are the way to specify our constraints. So you say, okay, so these numbers in the red mean that this is the same constraint for both men and women in this case, that you can have at most one person, one of each group in the first position, at most two, and so these are not really constraints. But starting from the third position, they start becoming non-trivial constraints. So this, this ranking, for instance, does not satisfy this constraint because at the position D, we have already seen 3 people who are men, and we were only allowed 2. And this is an example of, this is an example of a ranking which satisfies. So the question becomes how to find this ranking. That's the theoretical question. The unconstrained ranking problem is well studied. It's the maximum weight bipartite matching. And here, what we study is the problem of this constrained bipartite matching problem, where we identify this parameter delta. Delta is the maximum number of groups an individual can belong to. And it's interesting that the complexity of this problem seems to depend on this parameter. So these groups are intersectional. So for instance, if you consider both gender and race, then delta is equal to 2. If you consider gender, race, and let's say social status, then it becomes 3. And what we show is first that it is NP hard to find a better than delta approximation. And then under some reasonable assumptions on the utilities, we show that for delta equal to 1, which is the non-overlapping case, we get an exact algorithm. And when delta is bigger than 3, we get a delta approximation. we don't know what the answer to this question for delta equal to 2 is. It seems like a very challenging combinatorial problem, which if you're interested in, is a good one to try. We do assume something on the utility, which is that they satisfy this monotonicity condition and this what is called the Monge property. I don't know if you heard of it. It's a natural property. It's kind of arises in the stable marriage setting. And it's satisfied for all metrics that people care about in the world of rankings. The algorithm is very simple and nothing that I'm proud of other than the fact that it works and it's linear time. So since I have very little time, I'm gonna start concluding, Yossi, if it's okay. So I'm gonna skip this part. I'll, I guess, share these slides at some point if someone wants to look at them. Okay, so we have again a demo where you can play around with and see how on real world data, the difference between unconstrained and constrained bias is not so much. But here's a question, and this is the thing that I want to conclude with, is we talked about constrained optimization problems, and the question arises, does the overall utility really decrease? And we spend so much effort in trying to estimate the price of fairness, which is really the decrease in the utility. And the answer turns out to be surprisingly no. In many cases, or in some cases rather, constraints can mitigate implicit bias. And this is something that I think is worth understanding. So what is implicit bias? So implicit bias, we all have, not one, but multiple of them, is unconscious attribution of qualities or lack thereof to members of a particular group. For instance, it could be gender, origin, sexual orientation, race, or which university one comes from. And this is a factor that adversely affects groups in many societal contexts. I guess we have all heard about these things, but I'm sure if you look deep enough, we are all guilty of implicit bias as well, I guess. So this is one reason why the input to the algorithms could be distorted. And that's an observation which was made very clear in a recent paper by Kleinberg. I'm going to tell you what their model was. So in the context of rankings. So they studied the subset selection problem, but let me tell you that in the context of ranking. So what really happens is that there is a true utility of an individual, which is not known to the algorithm. Let's call that W sub I, okay? And V sub J is just the discount factor associated to position J. So the total utility of placing the individual I in position J is Wi times Vj. So Kleinberg-Raghavan considered the following model of observed utility, where they say there is a discount factor beta, which is the implicit bias factor. And they said that, okay, so the observed utility is, so there are two groups. So their model was for two groups, G1 and G2. So G1 was the privileged group and G2 was the underprivileged group. So what you see about G2 is not their true utility to you, but you see a discounted factor. And that discount comes from basically, I mean, if I'm the one who's viewing it, it comes from my implicit biases. And what this does is it essentially creates this distortion. And so if you use standard unconstrained optimization algorithms, you are playing into the game of this implicit bias. What we show, and building up on their results, so what Kleinberg and Raghavan showed, that once you add a natural constraint to the subset selection problem, once you add a natural constraint selection to the subset selection problem, you can actually increase the true utility, not the observed utility. Observed utility you cannot never increase because that's what you're optimizing. And that's something surprising because that tells you that this adding constraints can actually be helpful for everyone involved in this process. And that's what we formally established in this paper that appeared in this fat star. So we assume that the utilities are drawn from the uniform distribution, and we show that our constraints that we talked about in the previous few slides can recover the optimal latent utility as the number of positions go to infinity, number of people go to infinity. One of these, I forgot what it is. Okay, so I think this is something really interesting and something to be explored more. Oops. Okay, and so I'll just conclude by summarizing a few things. That human biases can creep into the world of algorithms through data and design choices, if not carefully thought. Biases can worsen existing societal biases and are different in different contexts. Still, algorithms can be designed to control. I think this area presents exciting new opportunities for TCS and machine learning researchers. I guess I talked enough about our contributions. So some future directions, I think, referring to the question somebody posed in the middle of the talk, is that all of the results so far assume that we know the group information correctly. When we do not know the group information correctly, there is a problem of that while adding constraints, you can actually make the situation worse. So we can actually observe that. If, let's say, you only know that with 80% probability and a person is a man, right? Adding constraints to enforce your fairness metrics can actually give you worse outputs than what you get without any constraints. And this is something, this leads to, at least in the world of classification, this has been studied, and we also have a recent work. This idea that inputs to the algorithms could suffer from implicit biases. So what kind of models we can come up for implicit bias and how we can design constraints effectively to counter them. How can we study the effect of downstream applications of these mitigations is also very important. This is a study pioneered by Kleinberg and Raghavan. And I guess one question which has totally not been studied as far as I know is what happens when the groups are dynamic. So we talked about groups being noisy, but groups are changing. Or the problem takes on an online flavor. So online and dynamic algorithms is a big, big area in TCS. But in the context of fairness, there are no formulations so far. So that's one of the great opportunities as well. I guess with this, I'd like to thank you all. Sorry for going a couple of minutes over time. I hope you found this talk useful.
Okay, thank you very much for your talk. And I think we risk to be unfair to the second part of the talk because we ran out of time. Nevertheless, I see at least one question that appeared in the second part of the talk, which asks what is if there is a relevance measure of diversity dimensions?
I'm not sure I understand the question.
Is there a relevance measure of diversity dimensions?
Maybe I can take it offline.
Yeah, okay. Another one just appeared right now. Regarding the vicious cycle from the beginning, could we imagine or model a situation where adding these fairness constraints would progressively reduce bias by acting on the original data in successive iterations?
That's a great question. I think, yes. The output of this algorithm is being fed and determined by the inputs. So adding constraints on the data, which could be thought of as adding constraints on the outcomes of the output or the inputs, will definitely try to curtail this vicious cycle. I think the only thing that I would say is that one has to be aware about the knowledge that we have about the problem. I mean, blindly applying these constraints, as I mentioned towards the end, can actually make the situation worse. If we do not know for sure each individual's group membership, we can actually make the situation worse than before. So in this, the more aware we are about our, where the input comes from, where the output goes, I think the better choices we'll be able to make about the appropriateness of the constraints.
Okay, thank you. Thank you again for your talk. Now we'll close the session.